I've mentioned earlier that the backward search is actually a graph search, and here is how that works. Suppose we are given our planning graph with the ultimate goal in proposition layer pk. Then we go backwards through the graph and somehow find some sub-goals in this layer pj. And then we continue the search, and this may lead to a different set of sub-goals in our proposition layer pi. Now, suppose somewhere between pi and p0 the search fails. So we come across an action layer where we try to identify actions that achieve all the sub-goals, but these actions are mutex and therefore we cannot find an appropriate set of actions. So the search has failed. Then what we can do is we remember that in layer pi we had these three nodes here that together were not achievable. So we continue with our backtracking process and we go back to layer pj, but then from there we need to find different actions, we go through different combinations, and we may up in our layer pi again, choosing in a different way the same combinations of preconditions or sub-goals in this layer. But since we have seen this combination of sub-goals in this layer before, and it was previously not achievable in the planning graph, we know that it still can't be achievable, so we don't need to do the search again. So effectively what we do is remember the search states we have encountered and where we have failed. That is, each search state is a set of sub-goals in a specific proposition layer, and by remembering these search nodes we effectively do a graph search. And we could just throw all these nodes that we want to remember into a big hash table. But here's a more efficient data structure that helps us remember what we've seen before, the so-called no-good table. The no-good table, denoted by this symbol here that looks like an upside-down triangle, or as the Greek letter nabla, is for a planning graph up to layer k, consisting of an array of k sets of goal propositions. So we have k layers in our planning graph, and our array also has length k, which means each of the elements of the array is for a specific layer. And then in each layer we have a set of goal propositions. The inner set is one combination of propositions that cannot be achieved. So that effectively is a sub-goal, one search node that we've looked at before. The outer set are all the combinations that cannot be achieved at that specific layer. And there are really only two types of operations we need to do on this data structure, namely, before we are searching for a sub-goal G in our proposition layer Pj, what we do is we look in our no-good table to see whether we've encountered the sub-goal before. And remember, we only store those sub-goals where we have failed. So we have to check whether our new sub-goal, the sub-goal that we're currently looking for, is in nabla of J, so whether it is in the Jth layer and we failed here before. If it wasn't in that layer, then we have to search for this set G in this layer Pj, and this will either succeed, in which case we have found a plan, or it will fail, and then we have to add our sub-goal to nabla of J, remembering that this is a sub-goal at which we have failed before in the Jth proposition layer. So the mutex relation for each proposition layer gives us pairs of propositions that cannot be achieved together. The no-good table goes further, as it gives us sets of propositions that cannot be achieved together in this proposition layer. Okay, now it's time to put all this into pseudocode. And this is the first of two functions that we will define to perform the backwards search. The function extract takes three parameters. The first parameter, capital G, is the planning graph that we've generated through our forward expansion mechanism. The second parameter is the goal that we are currently looking for. This is originally the overall goal of the planning problem. And finally, the parameter I tells us where in the planning graph we're looking for this goal. And we're looking for it in the ith proposition layer. Then the first thing we do is we check whether the layer we're looking at is our proposition layer P0, because that means we have reached our goal, so to speak, and we can return the empty plan. If this is not the case, then we have to use the no-good table, and we check whether our current sub-goal is in the no-good table at layer I. If this is the case, we failed here before, and we can return failure again. If we haven't seen this sub-goal g in layer I before, then we call our function gpsearch, that I'll explain to you in a minute, which extracts a plan up to layer I from our planning graph and returns that plan. So this can be either a layered plan or it can be failure. If it's unequal to failure, so if we found a plan, then we simply pass this plan through, we return this plan. Otherwise, this is the case where we've seen our sub-goal g for the first time, we've tried to search for it and we failed. So that means we need to update our no-good table and we add our sub-goal g to the no-good table at layer I. And then we simply return failure because we haven't found a plan at this point. So as you can see, most of the work is done in this function gpsearch, and that's what we will look at now. The function gpsearch takes 4 arguments. The first argument is the planning graph. The second argument is the goal we are trying to achieve in layer pi. So I identifies the layer in which we try to achieve the set of goals. And pi are the actions from layer AI, the action layer AI, that we have chosen to add to the plan. And as we have just seen in the definition of the function extract, what we actually pass in here are the planning graph, then the original set of goals in that layer, so that's all the goals in that layer, the empty set, so we start with no chosen actions, and of course the layer I in which we're doing all this. Then the first thing we do in this function is test whether the set G was empty. That is the trivial case, and we will deal with that later. First, I will look at the case where G contains sub-goals that we need to achieve in layer Pi. And if this is the case, then we select one of those goals, and this is denoted by the proposition P here. And then the next step is we use the positive effect links to choose a provider for this proposition. And a provider must be, as I just said, a positive effect, but it also cannot be mutually exclusive with an action that we've already chosen in our set pi. So this says there must not exist an action A prime in our set pi such that A and A prime are mutually exclusive in action layer AI. So this is the set of all actions in AI that we could use to achieve P, and we call this set the providers. Now, if the set of providers is empty, then we can return failure. So that means all the actions we found in the action layer AI were mutually exclusive with action we already selected, so we can't choose an additional action that would give us the proposition P. In that case, we return failure. But if we have one or more actions that can provide P, we need to choose one of them. And this is actually the choice point where our search branches. That means we may need to come back here later when we do backtracking and try out a different action to provide P. So this is our backtrack point. But now we have chosen A, and that means we can recursively call gpsearch. We keep the same planning graph, of course, but now all the positive effects of our chosen action are no longer goals that we need to achieve. Of course, P will be one of them, but there may be multiple positive effects that can now be removed from our goal. Then we add the chosen action A to our currently chosen actions in the set pi, and we continue to search in layer I. That means every time we go through this part of the algorithm, we reduce the set G, and eventually we will come to the point where this set G is empty. We have no more sub-goals to satisfy in this layer, and we have chosen some actions accumulated in the variable pi. Then what we can do is we call extract as shown here. So we give it the same planning graph, and as a new sub-goal, we give it the union over all the preconditions of the actions in our set pi. And we search for those in layer I-1, so in the preceding proposition layer. And this will return either a plan or failure. If it did return failure, then we simply pass this through. And if it returned a plan, then we need to concatenate this new layer, this new action layer, the chosen actions in this action layer to this plan, and return this as the result of the function. And that concludes the backward search through our planning graph.